Good afternoon. My name is Rrezarta Krasniqi, and it is a great pleasure to present today our topic, a hierarchical topic modeling approach for recommending repair of quality bugs. So quality bugs are difficult to detect because the implemented features are scattered across code base, and the scattered information generally prevents software developers from holistically understanding the root cause of quality bugs. So the traditional way of view of a system does not support a hierarchical code view for monitoring and tracing how quality features are topically related and how do they actually interact with each other. So we provide here an example, a very schematic view of quality concerns, which are scattered across three classes. So in this example, as noted in the color-coded areas, even though classes carry specific functionalities, each indeed captures several cross-cutting concerns across the code base. So if we look closely at the class A, it comprises the security logging functionality with enforced features, but unfortunately this is broken. So the yellow area, but then this yellow area is propagating in other classes as well, which means that other classes are being affected as well by this security issue. So dealing with this problem when faced with a highly complex project that contains thousands of packages and classes with thousands of lines of code, rationalizing and locating all relevant classes and their relation to quality concerns can be an unfeasible task. And therefore, the use of hierarchical representation facilitates this process of detecting complex relations among different classes, such as inheritance, composition, or even aggregations. So basically, our approach consists of three layers. From general point of view, we extract the low-level quality-related features from a collection of related classes or artifacts such as code commits and source code, and systematically construct a quality feature-based hierarchy tree to detect high-level quality concerns that potentially affect several other classes. So we construct a hierarchical tree that forms clusters from a set of related classes, such as an example before classes A, B, and C, that convey similar topics so that a new bug can be addressed. So now, looking at specifically at each of the component, our approach consists of three layers: the artifact layers, the structural and textual analysis, and topic generation. So one of the first ones are the inputs, and the second one basically is where we perform the processing of code and commits. So first we construct the AST and the code parser for the source code part. So the AST basically what it does is that it extracts most informative code elements such as method variable names, parameters, and so on. And for the parsing steps, we perform tokenization on naming convention, remove stop words, or remove programming special keywords such as end-to-end operations and so on. And then for the code commits, basically we extract code commits from GitHub, and then we also parse that information to a readable format. As you know, not necessarily all code commits are very clean, so this part is very necessary. And then for the other step is that we're also using third-party tools to facilitate the process. So we built actually a classifier that is intended to, actually this is our previous work, where we automatically can detect an arbitrary bug, reported issue tracking, whether it's security related or other issues such as performance or usability concerns. And then after that, we also built another trace link meta model, which is actually supposed to tie and connect all these different artifacts of bug reports with the past history of data. And then the most important part where we actually get into our algorithm is the hierarchical quality topic meta model that we have built. So going to this part, which is the most important one. So we built two matrices. So first matrix, the M1, constructs the relation between quality topics detected in the classes, code commits, quality concerns. Then we employ hierarchical topic modeling, HDP model, for aggregating low-level code features into source code to infer quality concerns at the high level. And next, we organize classes for each quality type or mixture of quality types. So as depicted on the left side of the figure, each of these cells in M1 here describes the content of each class and their corresponding code commits affected by quality concern. And the greener the cells in M1, the more those classes contain quality-related content, which is measured by keyword probabilities found in code. If classes do not contain quality-related information, the M1 cells are empty, such as in that case, classes are purely functional. And so now, this is actually the part where we do HDP, and this is the part where we are using our existing tool or classifier for detecting whether bug reports are either security or performance related or not. So either they contain information about quality concerns or not. And even for that, we extend and create basically the same results reported, we actually transform them into a matrix 2. So now we can derive the relation between quality concerns detected in the source code and quality concerns detected in the bug report. And that now, to be able to relate the relations between them, we create a VCM text similarity model, and then that would be able to match which classes or concerns are potentially the ones that are going to be affected or potentially capture the quality concerns that this bug report most probably needs for resolving. And so that is the VCM. So VCM that we discussed it, and that part is the final part of the algorithm. And then now going back to the methodology that we have used to conduct this study. So we conducted an empirical study considering 2 key research questions and 3 sub-questions. We selected 2 most related approaches as comparing approaches, such as a baseline using the LSI and the state-of-the-art using the LEA. So we used the gold set of 5,400 already fixed bugs from our previous paper and cross-checked them against the results returned by our approach. And finally, we performed the quantitative analysis using precision recall and F1 for comparing our approach against the baseline and the state-of-the-art. And then we provide 3 types of visualization for tracing suspicious buggy classes into 2D and 3D representation. So the key questions that we ask is that to what extent can SoftQualTopicDetector accurately detect quality concerns scattered across the code base to infer bug fixing candidate classes? And the second one is that to what extent can SoftQualTopicDetector support comprehension of quality concerns in code if various levels of code visualization are integrated? And then from that, we derive 3 other research questions, which focus mostly on the comprehension part of detecting or visual comprehension part of the of our tool. If it can support visualization, it's actually much better. So we provide 3 types of visualization to be able to depict quality concern visually. So basically, what of the things is we've done is that we focused on 6 quality concerns that are most commonly studied and also seem to be more relevant for developers to focus on. And those are performance, maintainability, portability, reliability, usability, and security. We used 6 different projects from 2 different tracking systems, such as Bugzilla and Jira. And so we actually use the data from our previous published work in SANER 2021. And you can see, if you're more interested to go into look into the way how we labeled our data set and the catalog that we formed, then we're more welcome to look at this paper. So then comes to a point where we actually have to compare our approach against the baseline and state of the art. So the baseline that we use was the work of Pojianik and then they basically use the LSI. And then the most recent work is from the work of the Gopalakrishnan. from a paper published at IEEE 2017, where they are using the LDA. And then comes our approach, where we actually are using as the key or the main algorithm, the HDP, the hierarchical Dirichlet process topic modeling. And then in addition, we're also using intermediary techniques of machine learning, information retrieval, and VCM. So then come the results. So basically, our results have proved or shown that our approach actually does much better than baseline and state of the art. It actually reaches precision of 84. And then a recall of 82 in regards to detection of specific quality types, or our approach reaches a high 90% in detecting performance bug and security bugs. So the other thing as we wanted to focus was trying to monitor what portion of code has been affected by quality concerns. So for this, we use the tree map view that our SoftQualTopicDetector can support for monitoring quality concerns affected by quality bugs. As shown in this figure, the color-coded areas show the type of quality concerns of the affected features at the package level in the main hierarchy. So the tree map view feature in our tool could visually delineate the number of classes affected by quality bugs. For instance, in this class, one of the most affected package was the one from containing performance bug, and that actually consists of 65% of the classes affecting that package, and that is pretty much 115 classes to be precise. But then there were also other packages, such as maintainability, which actually only was affected 2.2%. Next, we provide here the hierarchical view of which is a visualization feature of our tool that can support for prioritizing quality concerns based on their impact on the code base in terms of number of classes being affected. For example, the figure here, the hierarchical cluster generated by our tool, showed an interesting and informative outcome about the Derby project. For example, based on the observations that we got, quality bugs naturally fell into 6 categories of clusters, with performance quality bugs to be the dominating one across the OS Derby project. So the orange rectangle here basically showed the top hierarchy of performance concerns to be the most dominating ones for topic 3, 5, and 6. And it's affecting multiple classes. So the darker here, in this case, the darker brown color showed the higher number of classes affected. And then in these two tables, for example, we showed only 2 instances derived from the hierarchy due to space limitation. But for example, quality topics labeled by topic 3 generated by subtree 1, and quality topic labeled 5 generated by subtree 2, and for candidate classes to address P1 bug, which is referred to, P1 bugs are usually referred to bugs that typically need an immediate fix within 24 hours. And then finally, we provide the city view. Basically here we use our tool in addition to a third-party tool called the Code City, and then provided this city view in visualizing all the potential quality concerns affecting different packages. And we provided this 3D-dimensional view because it just gives a whole holistic view of which part of packages are potentially affected by quality concerns. And then to give away the practical applicability of our approach is that it provides immediate actionable auditing insights to software companies for handling security concerns or even performance and reliability concerns. It provides early prevention of human catastrophic events by detecting reliability, security, usability concerns, among others, at the implementation level. It also provides enhanced traceability of highly impacted quality concerns during maintenance and evolution. And finally, software developers can gain a breadth of understanding quality concerns, which leads to improvement and facilitation of debugging process, and also reduces system cost overruns for the company as a whole. And thank you. This is all. I would be very happy to take any of your questions.